Hi folks, so welcome to part 2 of our excursion into the Doppler Effect, and now we're going to introduce you to some problem solving techniques and also some conceptual understanding of typical exam problems as well as problems related to everyday life. So for this we'd require that bling that we introduced you to. Just recall that formula, and we're going to manipulate that formula to get a quantitative feel for the change in frequency, or what we would call the pitch of the sound signal. Right, so just for a little warm-up exercise, we're just going to introduce you to something very, very simple, and then we'll move on to the more, of course, difficult stuff. So here we go. Calculate the wavelength of a sound wave given off by stationary. So you've got to be very, very careful with words here. Stationary fire truck, if the frequency of the waves emitted 1,000 hertz, take the speed of sound in air to be 340 meters per second. So if you look very carefully, it'll be nice to write down what's given in the question. So I always like to write down given and identify. Firstly, we know the truck is stationary, so we don't expect any change in frequency or pitch. That's based on the physics. So we're given that the frequency of the source is 1,000 hertz, and the speed of sound in air to be 340 meters per second. So the velocity of sound, let's take that as v, is 340 meters per second. And what we need right now is really to work out the wavelength of this sound wave. If you recall from grade 10, the classic wave equation is v is equal to f lambda, and we want the wavelength. So if we make the wavelength the subject of the formula, we divide both sides by f, we get lambda is v over f. So it's a very simple matter of saying 340 meters per second divided by 1,000 hertz, and that would give you, say, 340 times 10 to the minus 3, if you want to call it, meters, which again, if you look at it, is 34 times 10 to the minus 2 meters. Okay, so that's pretty straightforward, and there you have it. So 34 times 10 to the minus 2 meters, what would that be? That's like 34 centimeters. A pretty short wavelength for a fire truck, but yeah, but that's good enough. There's your answer, pretty straightforward. Right, so let's have a look at the next one. So here the truck is now moving at 30 meters per second, and it's approaching a man who's standing in the middle of the road. I don't understand why he's standing in the middle of the road, but there we have a truck approaching him at 30 meters per second. He's just standing there, so he's not moving. The frequency of the sound waves emitted by the truck observed by the fireman riding on the truck. Now, if you think very carefully here, it's the same truck as before, that's what we're going to assume, and we know that the frequency of the waves given by that truck, remember the source, recall, was 1,000 hertz. So if you look at the first question, the driver's in the truck, or the firemen are in the truck and they're riding with the truck. So relative to the truck, they are stationary. Does that make sense? Yeah. So that guy's sitting on the truck, and so the frequency that these guys would, the frequency of the listeners for part 1 would be the same as the frequency of the source, or the siren, which is going to be 1,000 hertz. I think that's pretty clear, pretty straightforward. The second part of the question, let's have a look at that very carefully. So this is part 2. The truck is moving towards this man who's standing in the middle of the road. So if I draw a little picture, not very artistic, but this is my idea of a fire truck, and the siren is blaring away there. The truck's moving towards the right, and there's this very brave, or some sense stupid person standing in the path of this truck, and for some reason he's all excited. So the velocity of the listener, let's put it that way, would be 0, right? And the speed of the truck, if you think about that, is 30 meters per second. So that's all we have for now. So, and if you look very carefully, let's look at the interpretation. As the truck approaches the stationary man on the road there, the distance between the truck and the man is decreasing. So what do you think is going to happen to the sound waves as the truck approaches the man? Think of the word bunch. The sound waves bunch up. And if the sound waves bunch up, will the frequency as perceived by the man increase or decrease? Would it be a he or would it be a ho signal as the truck approaches the man? Right, so it's pretty straightforward. We know it bunches up, and the fact that the sound waves are bunching up, you would hear a higher frequency or perceive a higher pitch, which goes he. Okay, higher frequency. But for us, we need to know as a physicist, what is the actual change in frequency? So if the sound waves is, the note is 1,000 hertz, it has to be greater than 1,000. But what exactly is that number? And that's what we're going to try and find out. Let's just continue with the same problem. And so we have the truck traveling at 30 meters per second approaching a man who's stationary. Now recall the bling. Here we go. That's the bling over there, right? So let's try to interpret each of the terms in the formula. So FL, that is the frequency perceived by the listener of the sound note. Fs is the actual frequency of the siren. V is the speed of sound. Very important to know these things. VL is the speed of the listener, and Vs is the speed of the source. So as we read this question, it also tells us the speed of sound in air to be 340. So just write that down very quickly. Don't assume that it's always 340. You've got to read the question very carefully. 340 meters per second. We know that the listener is stationary. So if he's stationary, it's 0 meters per second. That simplifies a lot of things. The source, the truck, is moving at 30 meters per second. And we have one more thing that they keep leaving out in the question, but the frequency of the source is 1,000 hertz. And that continues from the very first question we started. So what are we solving for? If you look at the quantities, the unknown is FL. So it's just a matter of substituting into that formula and then using a calculator and simplifying. The problem is, which signs do we choose? Now this is very important, plus or minus. So that's the key to the entire thing. If you can determine the signs, then you're on your way. So I just want to write down that bling equation again. It's V plus or minus VL all over V plus or minus Vs. I like to put that in brackets times Fs. So we know straight away from what's given that the listener, that's going to be 0. So this would simplify immediately into V all over. Now you've got to be very careful here. At the bottom is V something Vs. Do we use a plus sign or do we use a minus sign? So forget about the listener. Let's look at the truck. Okay, the truck is now approaching the listener. So the distance between the listener and the truck is decreasing. We know the frequency is going to go up. So if we want the frequency to go up, we better be dividing by a smaller number. Because if you divide by a bigger number, what's going to happen to the frequency? It's going to go down. So for example, if I asked you a very simple question, which is larger, 1 over 4 or 1 over 5? 1 over 4 or 1 over 5? Well, let's say, well, come on, 4 is less than 5, so 1 over 4 must be greater than 1 over 5. And you'd be right, because 1 over 4 is 0.25. 1 over 5 is 0.2. So if we want a smaller number in the denominator, we have to put a minus sign. Do you agree with me? That actually means we'll be dividing by a smaller number. If we're dividing by a smaller number, then that smaller number which basically means dividing by a smaller number, the result is 1 over that smaller number. It's going to be a larger number. This is not a maths lecture. This is pretty obvious, but I'm just stressing the point is how we choose the signs. Well, let's just put in the numbers and just see what actually happens. So the velocity of sound was 340. Then we go 340 minus the velocity of the source is 30. And we multiply that by 1,000. And let's have a look. So we get 340. What is 340 minus 30? Come on, you don't need a calculator for that. That's 340 over 310. 340 divided by 310 equals that. Multiply that by 1,000. And for a show as God made little apples, what do you think this number is going to be? It turns out to be 1096, approximately 1096 hertz. And ta-da! 1096 is greater than 1000. Increase in frequency, higher pitch. He, not ho. There we have it. Perfect. Thank you very much. Okay, let's have a look at another one. That was pretty straightforward. So this one, let's have a look. Okay, fire struck stationary, very important. Stationary means not moving, it's at rest. Sounds its siren at a frequency of 1000 hertz. Finally 1000 hertz. Calculate the frequency of the sound waves perceived by a man standing in front of the truck. So standing in front of the truck. And then 2, the frequency perceived by a girl standing behind the truck. Oh my goodness, what's happening over here? So the truck is stationary, nothing's moving. Let's draw a little picture. Well, I'm an artist of note. You realize that, hey? Whoa, here's me fire truck over here, and it's sending off its signals out there. And there we have the very brave young man who's standing in front of the truck. And then we have a young lady who's brave enough to stand behind the truck. Right, so now let's analyze the situation here. Truck's giving off a sound wave, so they're going to go out like this. And it's going to go out like this at a frequency of 1000 hertz. So my question to you would be, whether you're standing behind the truck, in front of the truck, on the truck, under the truck, because everything is stationary except for the sound waves, what frequency would you expect to perceive as this fire truck emits sound waves? Come on, it's pretty straightforward. The frequency of the listener behind the truck or in front of the truck should equal to the frequency of the source, the siren. And so we wouldn't expect the signal to be Doppler shifted. If you do, you got to please give me a call and explain to me how that is possible. That would indeed be a very interesting problem for me to look at. Yeah, so that's a great invitation, but hopefully you see that it's going to be 1000 hertz. Nothing's moving, no Doppler shift. Okay, so on to the next question. And here we have a stationary truck and we have a moving observer. So in this case, we have a truck that's stationary, emitting a sound signal at a frequency of 1000 hertz. And we have a very determined person walking towards the truck. Look at this guy. Yo! And he's walking at a speed of 1.6 meters per second. We know the truck is stationary. So it's nice to always write down what's given in the question. So we know that the source, Vs, this guy, is 0 meters per second. Nothing's moving. We also know that the listener in this case is moving at 1.6 meters per second, given here. We know the frequency of the source, Fs, is 1000 hertz. We also know the speed of sound. We're going to take as 340 meters per second. So what we're really looking for is the frequency of the listener, which is that over there. So if you write down that formula, we're going to have something like FL is equal to V plus or minus VL all over. Now watch. We know Vs is 0, so this is just going to be V over V times the frequency of the source. Now watch very carefully. If the guy is walking towards the fire truck, the distance between the truck and him, this is going to be decreasing. It's going to be a bunching of the sound waves. And what do you think? Bunching of the sound waves, increased frequency means higher pitch. Is that right? So we want the frequency of the listener here to be greater than the frequency of the source over there. So do we use a plus sign or a minus sign now in the numerator? Well, if we want a bigger frequency, we better be multiplying Fs by a bigger number, at least greater than 1. So it would be interesting, and I think you'd agree with me, that we have to use the plus sign and not the minus sign. So in this case, we're going to go V plus VL all over V times Fs. Let's put in the numbers. V was 340. Its speed of sound. The listener is moving at 1.6 all over 340, and the original signal was 1000 hertz. Now that's 340. If I do that plus 1.6 and we divide that by 340 equals to that, and we multiply that by 1000, and here we go, 1004. We don't expect a very massive shift, but it's about 1004 hertz. But nevertheless, you must agree with me, 1004 hertz is greater than 1000 hertz as expected. So that's perfect. Okay, so let's see what we've got over here. It seems like this guy is walking away from a stationary fire truck, which is sounding off its siren at a frequency of 1000 hertz. So straight away, conceptually, let's just see whether we understand what's happening. As he walks away, the distance between the truck and himself starts to increase. And if the distance increases, we know this, then the waves should basically start to spread out. Okay? And the spreading out of these waves really results in a reduction of the frequency, and hence the pitch must be lowered. So essentially what should happen is our final calculation for the frequency perceived by this guy walking away from the truck should be less than 1000 hertz. So as per usual, let's write down what's given. We're given the frequency of the source. Here we go, 1000 hertz. The truck, the speed of the truck is going to be 0. The truck is stationary. It's not moving. Stationary. The listener, of course, is moving at 1.6 meters per second. And the speed of sound is 340 meters per second. So what is the question asking us? It's asking us to work out the frequency as perceived by the listener, or what I would like to call the observer. So if we write down listener is equal to V plus or minus VL all over V plus or minus VS. And I like to put a nice big bracket over there, times Fs. So from our observations of what's given, we know the velocity of the source is 0, so that's gone. We're not dividing by 0, it's just that is 0. And what's interesting here is walking away. If he's walking away, do we use a plus sign or a minus sign at the top? We want a smaller number because it's going to spread out. So we got to take the difference. So it's going to be a minus sign. So finally, we can write this. Let me write this out here. The frequency of the listener is V minus VL. That's relative velocity over V divided by the frequency of the source. Let's put in some numbers. So we're going to get 340 minus 1.6 divided by 340. And what was the frequency of the source? Let's change the color into this beautiful blue, 1000, and let's see what that comes up to. And we know that it must be, and we can see this straight away, minus 1.6. Okay, Work this out, and then we multiply that by 1,000, and we end up with 995 hertz, which is less than 1,000 hertz, as expected. Why? As he moves away, the sound waves spread out. There's a reduction in the frequency, and hence the pitch should also be lowered. And there you have it. Beautiful. Of course, we must have a look at the most general case, where now we have moving source and moving observer. So you have a police car moving at some speed, Vs, sounding its siren, and you have a robber, and he is moving at some speed, VL, away. So he's moving away. Of course, the car will be moving towards him. Why would the police car be moving in the opposite direction? So let's bring out our Bling equation that describes the change in frequency, and let's just try to analyze rather than do a calculation. We're going to handle it from two parts. We always say that the top of this belongs to the observer, and that's the way I like doing this. This is the observer, or what we would call the listener, and the bottom there belongs to the source, the thing that's giving off the sound signal. So if this guy, let's just separate this out carefully. If he's running away from the car, forget about the car moving. If the robber's moving away from the car, right, the distance between the car and the robber should, in principle, increase, so the wave should spread out, resulting in a smaller frequency. So do you think we're going to use a plus sign or the minus sign in our calculation? We want a smaller number. So would we add at the top, or do we subtract at the top? That's pretty obvious. We have to subtract because we want a smaller number. Perfect. Okay. Now, let's forget about the robber. Let's move to the source. Is the source moving towards the listener or away from the listener? Well, it's pretty obvious from this picture. The source is moving towards the listener. So if the source is moving towards the listener, irrespective of whether he's running towards the car or away from the car, what the source is doing is closing down the distance. So that should result in an increase in frequency. So if it's an increase in frequency, and we're looking at the denominator, would we want a smaller number in the denominator, or do we want a bigger number to produce a bigger frequency? Right, as we established earlier, because in the denominator we want a smaller number to get a bigger frequency overall, and the way we do that is to use the minus sign. So for this scenario, for a robber running away from a police car, you must agree with me, the listener, the robber, would perceive this frequency over here. Both minus signs. Why? For the top is running away, so he'll perceive a smaller frequency if the car was stationary. But the car is moving, and so to take care of that, let's look at the denominator. The car is moving towards the observer, which is the robber in this case. So if he's moving towards, the distance is decreasing, so we use a minus sign because the overall frequency from that point of view should be larger. So the combination of robber running away and car moving towards the listener actually ends up with a situation like this. And if you put in numbers, like maybe take the listener running at 1.6 meters per second, take the velocity of sound to be 340 and the velocity of the car to be about 340, and say the frequency of the source is 1,000. Put in some numbers and let's basically see what you get. That's the only way you're going to understand this, is by actually playing around with the mathematics, changing the subject of the formula. And they're not always going to ask you to work out the frequency of the listener. They could ask you to work out the frequency of the source. They could ask you to work out the velocity of the listener or the source. And that's also very interesting. And that will be coming up in our next video. So can't wait to see you on the other side of 1210, whatever that means.